Hi, welcome to your lesson on the definition of a logarithm. Let's begin with the definition of a logarithm. The definition tells us that we can turn any exponential statement into a logarithmic statement. Here we have b to the power x equal to y, or is y. This in logarithmic form changes to x equals log base b of y. Notice the base here is b, and in the logarithmic statement this is called the base also. It is also b, so b is the base in both cases. All right, and when you change the log form, the exponent here is what the log is equal to. So the log statement is equal to the exponent of this statement here. So using that definition, another way to look at it here, we can read this as log base 5 of 125 is 3. But to read it in terms of what it means, you would read it like this. The exponent that 5 must be raised to get 125 is 3. So looking at that statement that way, here we have it again. That is equivalent to this, because this again is telling us the exponent that 5 must be raised to get 125 is 3. So the exponent that 5 must be raised to get 125 is 3. So these two statements are equivalent. Log is just another way of rewriting an exponential equation. Let's apply it. Here's some examples we saw in class. We're just going to recap. Here we have base 3 and an x. If we want to solve x, we need to get x out of this statement here, right? Anytime we want to solve for x in an equation, we want to isolate x. So this one we can change to exponential form, which is 3 to the second power equals x. And that makes it easy to solve. X equals 9. Here we have x within the log as well. So if we want to solve for x, we need to isolate the x. So let's write it in exponential form as well. X to the negative fourth power equals 16. Anytime you have an exponent and you want to get rid of it, you can multiply the exponent by the reciprocal fraction. In this case, that would mean applying negative 1/4 power to this, because these negatives will cancel, and that 1/4 will cancel that 4 also. If we're applying that exponent on this side, we have to apply it on this side as well. So again, these two cancel each other, because negative 4 times negative 1/4 is 1. So we have x to the 1, which is just x. Over here, we have a negative exponent, so I brought that to the denominator. And 16 to the 1/4 is actually the same as the fourth root of 16. And the fourth root of 16 is 2. So therefore, we have x equals 1/2. In the last case here, we have a log statement. If we were to simplify this log statement, of course, you could punch it in a calculator, but using just what we know about exponents, well, first of all, what does this equal? Well, it equals some unknown value, which is x. All of this is going to equal something which we don't know yet, so we're going to put x. Let's change it to exponential form. 5 to the x power equals 625. We know that this is a form of 5. 625 is actually 5 to the fourth power. Now we know, since these bases are the same, that the exponents must be equal, so x must be 4. Therefore, what that tells us is that this original statement must be equal to 4, because all of that we said equals some value x, and now we found out what x is, so we can say all of that equals 4. All right, time for you to take some notes. In your notebook, let's add some examples first. So our title is applying the definition of a logarithm. We have this simple one to start, but let's solve this. Again, x is hidden within the log statement, so we're going to change it to exponential form in order to take x out of that log. So 7 squared equals x. That means x must be 49. All right, let's look at another one. Here we have 2 to the x power equals 50. Again, x is within the exponent here, so let's use a log to bring that out. Let's change this exponential form to log form. We're going to actually use something called the change of base formula here also. How the change of base formula works is when we have a log of some base and we want to change that base to some other base. Notice the base has changed to c here from a. Then we create a fraction of logs with this number being the top one that log is taken of, and this number here being on the bottom where log is taken of that. Let's see how that is applied. So here, this in log form would be log base 2 of 50 equals the exponent, which is x. Now this, you could punch in your calculator, but sometimes it's tough to work with logs of a base other than 10. 10 is your normal base for a log. It's like your standard log. So why don't we change this to log base 10? Here's what it would look like. We have log base 10 of 50. So that number always goes on top, divided by, and then log base 10 of this number. So log base 10 of this number divided by log base 10 of this number. We could make this base any base we want, but again, 10 is like a standard log, so we're going to put that in here. That equals x. On the calculator, see how we do that. So we have log base 10 of 50. Again, is just a standard log. So notice when we punch log on our calculator, it just says log. It doesn't have a base. When you see just log, you assume it's base 10. Again, that's like our standard log. So we can do log of 50 divided by log of 10. Sorry, log of 2. So that gives us 5.64. All right, so the answer is 5.64. Now let's confirm that this would give us the same answer, because these two are supposed to be equivalent to each other, right? This and this are just different forms of one another. So using the calculator again, on the graphing calculator, you can actually enter logs of different bases. Even though this button here produces a log base 10, we can use alpha window. It gives us this little menu of items, and I see log base here. So I'm going to use number 5. And it's going to give me a log of any base I want. So I can input the base. I'm going to put input a base of 2, and I'll put 50 in here. This should give us the same answer as when I punch this in, because these are the same. Let's see. All right, same answer. So that one, when we change the base, gives us this, and this one with that still using the base of 2 gives us the same answer. All right, last example. We have log base 7 of this equals x. I'm going to change it to exponential form. 7 to the x power. 7 to the x power equals this part. Notice we have a bunch of 7s. That should give us a clue that we're working with the same base here. This 7 is like an 7 to exponent 1. This one to an exponent is a half. All right, that would change to a half. Now we can combine these. Since we have multiplying of exponential expressions, we can add the exponents. 1 and 1 and a half is 3 halves. So now we have the same base that tells us this exponent must equal this exponent. So x must be 3 halves. So that means all of this is the same as 3 halves. If you punch that in your calculator, it should produce that same value, 1.5 or 3 halves. All right, now it's your turn to try some. This one says solve using a calculator. So try this one using a calculator. You will change it to log form first. Okay, hopefully you looked at that and you said, okay, I see log base 10 of 500 equals x. This can now be punched in our calculator. Let's see, log base 10 is just log, right? 100. And that produces 2.7 above 2 if it's rounded. So 2.7 is our answer there. All right, now you're going to try a few without using a calculator. So the challenge here is to work with bases properly and see what you can do. First one is this. Try to solve that without a calculator. All right, let's change it to exponential form. 4 to the x power equals this value. Since this says without a calculator, that tells us this must be a form of 4. And it is. So 4 to the x is 4 to the 5th power. This is actually 4 to the 5th power. Now what that tells us is the exponents must be equivalent, which means x equals 5. That means all of this must be 5. Let's just double check. All right, so this is log base 4. So I'm going to do alpha window, log of some base, do 4 here, and 1024. And it gives us 5, so it works out. All right, here's another one without a calculator. Try this one. It's going to be a little more challenging. A hint here, or just a reminder, we see no base here, so you know that's log base 10. When you see no base, it is 10. All right, so let's try that. Okay, this one, let's change the exponential form. We have 10 to this power, 10 to the x equals this decimal. Now, again, without a calculator, that means this must be a form of 10. And if you remember your rules of scientific notation, when you have a very small decimal number, to change it to a power of 10, we slide that decimal over, we count, and it turns out that 10 has, the decimal would have to move 5 times to get you right there. So this must be the same as 10 to the negative 5. And that tells us that x must be negative 5. The exponents must be equivalent. If you're thinking about that one and wondering why this turned to that, another way to look at it is like this. So we have 10 to the x equals that. But this is actually 1 over 100,000. To get this decimal, you would divide 1 by 100,000. And 100,000 is actually 10 to the 5th power. Now, if you brought that up to the numerator, you would have this. So that's kind of the background of why this becomes this. All right, let's try another one without a calculator. How about this one? Okay, here if we change the exponential form, we have 4 to the x power equals this root. And since we're not using a calculator, it's clear that our goal is to get this to be a version of 4. First, however, I'm going to rewrite this root as an exponent, 1/2. Now 256 is a power of 4. It is 4 to the 4th power. So we have 4 to the 4th power in there and a half applied to that. Now when you have parentheses, you multiply the exponents. So 4 times a half is actually a 2. So we have 4 to the x equals 4 squared. And the exponents must be equal, so x must be 2. So again, if you punch this in here on your calculator, x should be 2. And let's confirm. It's nice to check these things out and make sure everything works out. I'm going to do a window again and use log of base 4. And here we have a root, second root, 256. All right, let's see what that produces. And it is 2, which matches our answer. All right, that's good news. Everything works out. One last one. This one is with a calculator again. So we have exponential form. Let's change to log form. Log base 3 of 40 equals the exponent x. This can be punched in a calculator, or it can be done by changing base, right? So on our calculator, I see that answer. Let's try that. Alpha, window, log of base, and then we're going to put a 3 in there. 40. 3.36, that works. Okay, now let's try using change of base just to be aware of that formula conversion again. We're going to change it to log base 10, and then that number goes on top, this number goes on bottom. All right, division. If you punch that in your calculator, hopefully it'll give you the same thing. Let's try it one last time. Log, that means log base 10, like log of 40 divided by log of 3. 3.36, the same answer. So again, the base 10 there just means log. We don't have to use the 10, and we got the same answer both ways. All right, with that, you're ready to handle anything you see in the practice assignment. Practice is key for logs for sure. This assignment has lots more questions similar to the ones we just did. It'll give you a really good chance to build your log skills before we move on to more difficult topics. Good luck, you can do it.